The problem is when we have had situations like we just did on the worksheet. And of course, ran out of space right over there for my x. There. We have had to use blanks because we know the first step. The first step is divide both sides by 1,000. But if we're going to get x, we have to get rid of that e. And right now, we don't have any way to get rid of e because we don't know how to undo things that are being raised to an unknown power. If you look at that, the variable is up here in the power. So it's like, how do I even bring that down so I can do anything with it, you know? Well, that's what logarithms are for. Logarithms are to undo these unknown power situations. But we have to learn what a logarithm is. We have to learn to speak logarithm language. And what we're going to do today is really translation. That's what we're going to do. We're going to figure out how do you translate logarithms into something that makes sense, something we already know how to do. So what we're going to do is write and evaluate logarithmic expressions today. And we probably won't get to graphing. We'll have to do that one tomorrow. But this will be enough for today because once we get this set in our minds, things will go very well. So this says, what we want to do to start with is write the following numbers as a power function of either base 2 or 3. Now that means we're going to write it as 2 to the something or 3 to the something. Because this is all about powers and undoing powers, our first thing has to be to remember some stuff about powers. So if you still have your power chart and you want to use that to get started, you can do that. But you won't be allowed to use the power chart when we get to the test. So hopefully you can think through this. 16. Do we raise 2 to something to get 16 or do we raise 3 to something? 2. And for most people, 2 to the third is immediate right now. We've been doing that all the time. That's 8. So I would need one more 2. So that's going to be a 4. And there's that little 8. Do we raise 2 to a power or 3 to a power to get 27? That's a 3. What power? Third. 81. Do we raise a 2 to something nice to get 81 or do we need a 3? We need a 3. How many 3s? Well, let's check. 27, we already know is 3 to the third. So if we multiply that by 3, there it is. We just needed one more. It's 3 to the fourth. There it is. So we're going to use what we know about powers because powers and logarithms work together. You have to have one and the other one undoes the other one. It's kind of like, and I know it's hard to think of it this way, but addition and subtraction. You want to undo addition, you use subtraction. You want to undo powers, you have to use logarithms. So it's this whole backwards and forwards relationship. So what we're going to do is we're going to learn how to express all numbers as powers of a common base. And pretty obviously we're going to start off with some that we've worked with before so that we're not feeling like, oh yeah, 7 to the 15th, I know that. No, we just don't. So things that are pretty normal to us to start off with. So what we had to do was figure out a way to undo something being raised to an unknown power. And the essential understanding is the exponential function y equals b to the x is 1 to 1. So its inverse, x equals b to the y, is a function. So we want a function to start with, and its inverse is also a function. So we've talked about that before. Functions have special properties, and that's what we want. Now it says to express y as a function of x for the inverse, write y equals logarithm base b of x. Well, here's where we're going to stop and we're going to find out that this is not as horrible as it looks. So here's what you do. You're going to write right in the middle here, snail shell. Which seems to have absolutely nothing to do with what we're doing right now, but in a second. And then draw a little snail shell. You know, snail shells, like that. So snail shell's good. Like that. So, we have this. y equals logarithm base b of x, which makes no sense to us right now. So we would need to translate that into something that we understand, something that we've done before. So here's the first step. We're always going to put the logarithm part on the left-hand side. So this will say logarithm base b of x equals y. So there's step one, setting it up nice. And then what we're going to do is we're going to use a snail shell to do what's called exponentiating this. And that means we're going to make it look like a power, because we've worked with powers. All of chapter 6 was about powers. If we can make that look like a power, then it'll start to make sense. So your snail shell always starts down here at the base, and it will be b to the y equals x. That's what logarithm base b of x equals y means. It means if you raise b to the y power, you will get x. So if we can change this into a power statement that makes sense, well, then we can work with logarithms for a while until we get used to it and say, hey, wait a minute, so how would this work? So here's what we just did. We raised 2 to the third power, and that gave us 8. Now if I snail shell this, that's what this says. It just says it in logarithm language. That's all. So it's kind of like your first few days in Spanish. The Spanish teacher is talking Spanish up there, and you're looking at it like, you're crazy. We don't know this stuff. Right? We don't know what this is. So we break it down and we say, you know, we don't know this just yet. So what we're going to do is we're going to take this logarithm stuff and we're going to change it into a power statement so that it makes sense. Because 2 to the third is 8. But logarithm base 2 of 8 equals 3 right now, what on earth are they trying to tell me? So we're going to change those into power statements. So down here it says, key concept, logarithms. A, logarithm base b. Try and get that a little bit further up here. There we go. Of a positive number x satisfies the following conditions. First of all of our bases are going to be positive. We're not going to use 0 as a base because 0 to any powers is just 0. And b is not going to be 1 because 1 raised to any power is 1. So that doesn't make a lot of sense to do that either. So in logarithm base b of x equals y, that only works if, when you snail shell it, b to the y equals x. And that's the way that we're going to try to understand logarithms to start with. So like it says, you can read logarithm base b of x as logarithm base b of x. In other words, the logarithm y is the exponent to which b has to be raised to get x. And if we snail shell it, it will make sense for a while, and then we'll start to think that way. It's weird how, remember FOIL? How when we were trying to do the factoring and FOIL, we were using those motions of outside times outside and inside times inside, and our eyes got trained to that and got faster at it. It's the same thing here. If you're constantly doing that snail shell, then it starts to make sense. When you see log, you instantaneously think in snail shells, and that's what we're going to do. So logarithms, undo bases with unknown powers. That e that we wanted to get rid of earlier. That's something we can undo with logarithms, and we're going to want to undo with logarithms. Big box. The exponent y in the expression b to the y is the logarithm in the equation, logarithm base b of x equals y. Makes perfect sense. You snail shell it, b to the y equals x. The base b in b to the y, and the base in logarithm base b of x, the base stays the same. You know, the base is b. It doesn't change. It's either the b in b to the y equals x, or it's the base for the logarithm. It doesn't make any difference. It's still the base. So it doesn't change names or anything. And it says in both, b will not be equal to 1 and b will be greater than 0. So we're not going to talk about negative bases. We're going to stick with strictly some basics here. Since b is not equal to 1 and b is greater than or equal to 0, then it follows that when you raise this thing to a power, it has to be greater than 0. And then b to the y equals x if x is greater than 0. So the logarithm base b of x is defined only when x is greater than 0. Now they make this sound really, really bad. So here's what I'm going to do. I'm going to give you an example of what it is they're talking about. And what they're saying here, I don't have a lot of space. Is this. They're saying if we have logarithm base 3 of negative 27 equals y, when we snail shell this, it's going to say 3 to the y equals negative 27. There's no power that you can raise a positive 3 to get negative 27. It's not possible. So what they're telling us is this, it doesn't make sense if it's negative, and this is positive. And we're only going to work with positive bases. So if we get a problem where this base is positive and the number we're supposed to evaluate is negative, we're just going to say no solutions. We can't do it. It isn't going to happen. So because y equals b to the x and y equals logarithm base b of the x are inverse functions, what this tells us is if you use logarithms to undo an unknown base, they'll cancel each other out. So this says x. That's all it says. Because these two bases match. That's x. This also just says x. Because bases and logarithms of that base undo each other. They're inverses of each other. Now, where did logarithm come from? Historically, logarithm means things in other languages that it doesn't mean in English. And so at some point when they came up with the name logarithm, it made sense in Greek or whatever language it was in. For us, yeah, the logarithm thing is like, how did they do that? But it made sense for what they were doing at the time. So the first thing we're going to do is this. We're going to take some stuff that's written as powers, and we're going to change it into logarithms. So 100 equals 10 squared. So I think about my snail shelling, and my snail shelling always starts with the base. And again, the base doesn't change names just because it moves. So the base in A, that's the 10, because the base is what's being raised to a power. So there's my little base. And now I think about my snail shelling. So 10 to the something, well, that would be a 2, equals 100. So logarithm base 10 of 100 is 2. And if you snail shell it, it says 10 squared equals 100. What do we use for the base in B? 3. Snail shell, we're raising that to the 4th power. And it gives us 81. Now I'm making my bases kind of big here. They're supposed to be little subscript numbers, but I want to make sure you can see what we're doing as we go through these. Alrighty. 36 equals 6 squared. As a logarithm will be logarithm base 6. What goes on the other side of the equals? That leaves 36. Now the 36 is actually the number we're trying to evaluate. So in the future, here's what you're going to be given. You're going to be given logarithm base 6 of 36 equals. That's why the snail shelling is important. Because you say to yourself, 6 to the something is 36. What's that something? Oh, it's 2. The answer's 2. And then you'll write a 2 down. Oh my. 8/27 equals 2/3 to the 3rd. Logarithm, what's the base? And that's okay because it's positive. So it doesn't really matter that it's a fraction. It's all right. On the other side of the equals, we'll need a 3 to get 8/27. That looks really awkward, like I'm squishing things here. Spread it out a little bit. pretty basic, easy problem there. Logarithm base 3, other side of the equals 0, and we're evaluating the number 1. Interesting. So if this is a 1, 3 to the something is 1. Hey, if I made this base a 4, wouldn't this still be a 1 if this is a 0 over here? So no matter what, if we raise something to the 0 power, we're going to get 1. So that's a special case of logarithms when that happens. Now we start finding them ourselves. What is the value of logarithm base 8 of 32? Do you know it already? Well, then we don't know it, then that makes it an unknown. If it's an unknown, we should do that. Because now we can snail shell it. We could say, all right, don't really have a good understanding of logarithms yet, but I know 8 to the x has to equal 32. Has to. All right, now I don't want to use trial and error. So let's see, what do I know about 8? What do we talk about with 8 already today? Flip back. What did we make 8? Earlier in our notes, what did we do? 2 to the 3rd. Okay, so maybe, bless you, at 2 to the 3rd, raised to the x power, you just multiply those two exponents together. Oh, I better make that in 2 steps though. So if somebody's gone, they can see what it was we just did. Now we're going to be able to do this if, bless you, 32 is 2 to the something. Is 32 2 to the something? What would the something be? 2 to the 3rd is 8, 2 to the 4th is 16, 2 to the 5th is 32. I want you to look at my last line down there in the red. Do you agree with me that 2 is definitely equal to 2? Does that make sense? 2 is equal to 2. So it's not the 2's that we need to solve. It's the 3x that has to equal a 5. That's what we have to solve. These 2's are already the same. This says equals. We'd be done if we were just worried about the 2's. We're not worried about the 2's. We need the 3x to equal a 5 in order for this to work. They have to be exactly the same. Oh, we can solve that. That's one step, for goodness sake. We divide by 3. The answer is 5/3. Seeing is believing. I wouldn't want to punch that in, just to make sure. So let's see. We're saying that the logarithm base 8 of 32 is 5/3. But here's where we started. We said 8 to the, let's see if our 5/3 works. Hey, there it is. It works. So if we can get them to have the same base, then we can solve it and we can find it.
I think trial and error would be much faster.
5/3? Take a while. It'll take a while.
Maybe through
All right, let's go through some that are not as bad, okay? Now, logarithm base 5 of 125. Can you snail shell that one in your head and tell me what it is? Well, then let's do it without doing it in our head. Let's put the x over there and let's snail shell. Five to the something is 125. What's the something? It is 3. This is cool. This says 3. That's awesome. Let's look at the next one. Logarithm base 4 of 32. I don't know that one. So 4 to the x equals 32. Can you raise 4 to something nice and get 32 to pop out? Okay. So 4 is definitely a power of 2, right? So 2 squared to the x power, power of a power, we have to multiply. 2 to the 2x equals 32. 32 is 2 to the something again. What is it? 2 to the what? Fifth. Do we need to worry about the big 2's?
No.
Already the same. We need 2x equal 5. Well, just divide by 2. 5 halves. Come on, that is so cool. This says 5 halves. That's what that says. Math is like secret codes. This is cool stuff. Oh, fraction. Oh. All right, so 64 to the x equals 1 over 32. Well, if 32 is a power of 2, isn't 64 a power of 2? What power? Yeah, it'd just be 6. Because we said 32 is 2 to the 5th. We'd need one more 2. So this would be 2 to the 6 to the x, which is 2 to the 6x. Huh. How'd they get that 1 on top of that fraction? Yeah, it has to be a negative power. Remember, that's what negative powers do. So this was 32 to the negative 1, but we need 32 as a power of 2. What power did we raise it to before? The 5th power. So 2 to the 5th to the negative 1. Well, that's going to be 2 to the negative 5. Twos are already the same. That's not our job. Our job is, when does 6x equal negative 5? And we divide both sides by 6. And there's our answer. Negative 5/6. Now the hope is always that we don't have to use the calculator for these. So you kind of want to sit there and think, okay, I know 2 to the 3rd is 8. Multiply by 2 again, now I get 16. Multiply by 2 again, now I get 32. Multiply by 2 again, now I get 64. You know, and think that way. Because logarithms are how we undo powers. We're supposed to understand powers so that we can go further. Alrighty, next up, common logarithm. There are logarithms that show up a lot because of our number system. Our base for our number system is 10. Now what that means is, once we go through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we really just start counting over again. Because then it's 10 plus 1 is 11, 10 plus 2 is 12, 10 plus 3 is 13. And so since our system is based on tens, the common logarithm is logarithm base 10. But you're not going to see that when they want you to do common logarithm. It's just going to say LOG. Because if it's LOG, we're supposed to know that means logarithm base 10. Because that's the common logarithm. Like it says, it's common. It's the one that's used a lot because of our number system. So we can write a common logarithm, logarithm base 10 of x, as just LOG of x. And we don't have to put the 10 on there. Sometimes it's helpful to put it there because we want a snail shell, and other times it's like, I don't want to write that. You can have that. So many measurements of physical phenomena have such a wide range of values that the reported measurements are logarithms, and like it says, exponents of the values, not the values themselves. How long it takes for light to travel to Mercury. It's a long ways. That's a lot of zeros. So if you don't want to write it with all those zeros, you could either write it as a power with scientific notation, or you could use logarithms, and that's what they're getting at here. When you use the logarithm of a quantity instead of a quantity, we're using a logarithmic scale. So really big stuff and really small stuff will tend to use logarithmic scales. And the Richter scale is definitely one of those. The Richter scale is a logarithmic scale. It gives logarithmic measurements of earthquake magnitude. Earthquakes release something called ergs, E-R-G-S, and it has to do with the amount of energy that an earthquake produces. Well, an earthquake makes massive damage because it releases lots of ergs. And those ergs are numbers we wouldn't want to represent with all the zeros that we actually have to have. So if you look at this, you'll see we've got this little erg thing, and then they use these times 30 squared, times 30 to the third, times 30 to the fourth, and imagine how quickly that gets to be a very huge number. So the difference between a 4 and a 5 on the Richter scale is actually a huge difference. I grew up in Minnesota. Only one time during my life were we supposedly able to feel an earthquake. When I was in my teens, there was an earthquake in Minnesota. Nobody felt it. It was just that mild, you know. But people out in California, they would know the difference between, that was just a 2 we had the other day. The pictures hardly even rattled on the walls versus, oh my gosh, we had a 9. Everybody's gone. You know, those type of things. So this helps those of us that don't know anything about the Richter scale figure out exactly what's going on. It says, using a logarithmic scale, in December 2004, an earthquake with magnitude 9.3 on the Richter scale hit off the northwest coast of Sumatra. The diagram shows the magnitude of an earthquake that hit Sumatra in March of 2005. This little formula, the log of intensity 1 over intensity 2 equals moment magnitude 1 minus moment magnitude 2, compares the intensity levels of earthquakes, where I is the intensity level determined by the seismograph and M is the magnitude on the Richter scale. How many more times intense was the December earthquake than the March earthquake? So the question is, it's great that they're giving us these numbers, but it doesn't tell us what kind of impact this had on the ground. Was this a much huger earthquake, or was it less of an earthquake? Was it exactly the same type of earthquake? How do we know? Well, we take a look, and we see in the drawing that they're giving us a magnitude. So here's what we know. The formula said the logarithm of intensity 1 over intensity 2 equals. This is comparing the magnitudes. We're comparing the magnitude of the first one with the second one. And it said, in December 2004, an earthquake with a magnitude 9.3. So the first one was 9.3. And we're supposed to subtract what we have for the second one. And the second one's in the picture, and that's 8.7 over here. All right, so the logarithm of intensity 1 over intensity 2 equals, well, that's just 60 cents. $9.30 minus $8.70 would be 60 cents. Well, now what do? I don't know what logarithms do. Well, what logarithms do, remember, is sales shell. So if we're looking at this, and it doesn't have a little number for the base, they told us what that base is if it's not there. What is it? It's a 10. Now we can snail shell it. 10 to the 0.6 power is going to give us whatever intensity 1 divided by intensity 2 is. And that's what we wanted to know. How do they compare when you compare them by division? So it was 9.3 and 8.7. That sounds pretty close, right? I mean, those two earthquakes had to be about the same amount of disaster. But 10 to the 0.6 power, it was almost 4 times as powerful. For that little teeny change from 9.3 to 8.7, it was almost 4 times as powerful. It was a huge earthquake compared to the 8.7 earthquake. Huge. So a little decimal change makes a big, big difference. So those were bad enough. Now we've got Mexico, which is a little closer. I don't like the fact that they're talking about stuff closer to us here. In 1995, an earthquake in Mexico registered 8.0 on the Richter scale. In 2001, an earthquake of magnitude 6.8, Washington State. How many times more intense was the Mexico earthquake than the American earthquake? Well, 8.0 minus 6.8. And because of what we just saw, we know theirs was massively worse than ours was. So logarithm of that change in intensity, $8 minus $6.80. Buck 20. We don't have a base. So what's the base? It is 10. So 10 to the 1.2 power will tell us how these two compared. I have a feeling we're going to find out that our little earthquake in Washington State was nothing compared to what they had in Mexico. Almost 16 times as powerful. It was huge, absolutely huge, the difference between those two earthquakes. So using the logarithms, you can see there's a big, big change. Now, what are we doing for time? Because I'm going back to 5. Yeah, we better wrap it up. So Mr. Deskin's going to be here for you tomorrow. Oh, 43210, and I know they're not going to be high, but how do you feel about just the snail shell process and going through that? Yeah, it's something to get used to. But you know what? After you do it a few times, I think you're going to be just fine. So tomorrow we'll do Mr. Deskin will do the graphic portion with you.